Welcome to our discussion of the Simplex Method for maximization. So here we're going to learn how to use the Simplex Method in order to maximize functions that have constraints, which is basically what linear programming is all about. So just some background on the Simplex Method, because it does have some limitations, right? It's very useful when you have more than two variables that you're trying to solve for. If you only have two, you can solve those pretty easily with the elimination method or the substitution method. And what the Simplex Method does, it gives us a very systematic way of checking all the feasible corners of your convex region, but it does them in a systematic way that makes sure that the value of the objective function always increases until it finds that optimal value, i.e. it finds that maximum. Or no solution. So in order for these maximization problems to work, you have to have the following conditions satisfied. First of all, the objective function has to be a maximized function. Otherwise, it's not a maximization problem. All variables are non-negative, which is usually the case because we're trying to model things in the real world, and you can't have negative quantities of things. And then the constraints have to be of the form that they're set less than equal to something and less than or equal to a positive number. And that is really what forces you to have that convex solution area, that feasible region, right? So let's look at an example. A farm co-op has 6,000 acres available on which to plant corn and soybeans. The following table summarizes each crop's requirements for fertilizer/herbicide, harvesting labor hours, and the available amounts of these resources. So you can see that they need a certain amount of this herbicide/fertilizer. We're just going to call it fertilizer. They need 9 gallons per acre for corn, 3 gallons per acre for soybeans, and they only have, they have limited amounts of resources. They only have 40,500 gallons of the stuff to use. Because if they had as much as they needed, we really could maximize it to infinity because they could just use as much as they needed. Harvesting labor takes 3/4 of an hour per acre to harvest the corn, 1 hour per acre to harvest the soybeans, and they only have 5,250 hours of labor, right? Because they have a limited number of people. Then we have to know what we're trying to maximize. We're trying to maximize profit. So we have our objective function, which is the profit per acre of 240 for the corn and 160 per acre for the soybeans. And then the question is, how many acres of each should we plant? So the first thing we want to do is we want to write everything out in kind of our standard form so we know what to work with. So we've got our profit function, of 240x plus 160y. Obviously, we're letting x be the number of acres of corn that we plant and y be the number of acres of soybeans that we plant. Then we have the land constraint. We were told that there were only 6,000 total acres, so x plus y has to be less than or equal to 6,000. We have the fertilizer constraint, so we have 9x plus 3y, because you'll remember that 9 and 3, Then we're going to have 3/4 x plus 1y has to be less than or equal to 5,250. You'll also note that x and y are greater than or equal to 0, because you can't plant negative acres of something. So we've satisfied all of the properties that we need to satisfy in order to use the Simplex Method. Now the Simplex Method just uses your simple matrix methods, your matrix operations on these systems of equations. So we convert each constraint inequality to an equation by using a new variable called a slack variable. And you can think of each slack variable as representing the amount of that thing, that constraint that we didn't use, Because we're not necessarily going to plant on all 6,000 acres. So we have to have this slack variable S1 that's the leftover, Because we might actually maximize our profits by not planting on all of the acreage. Because you remember there's a kind of a law of diminishing returns where you got to spend more money on fertilizer and more money on labor, and at a certain point it might not get you more profit to add in another acre, And then the same goes for the rest of our constraints. We might not use all of the fertilizer, so we have that slack variable 2. We might not use all of our available labor, so that's our slack variable 3. And so you can see that by putting in the slack variables, we no longer have a less than or equal to. They all become strictly equals. Because if, this stuff was less than, when we add the slack in, it ends up equaling, right? That's the leftover bits. Now, our slack variables, we always assume, that they're greater than or equal to 0, because again, they couldn't be negative, because it wouldn't make sense to have, negative leftovers, because that would mean we used more than we had. So then, once we have all of our slack variables in place, we set everything up by this specific layout. You'll notice the last thing we do is you take the profit equation and you set it equal to 0 by subtracting these two things over to the other side so that P is positive. You want to leave P positive because you're trying to maximize P, so you want it to be a positive value. So there it is, right? So here's all of our constraint things listed with all their corresponding slack variables. And yes, you want them on a diagonal, because remember, they're different variables. Each column is supposed to represent a different variable. So here's our X column, our Y column. Here's our slack 1 column, slack 2, slack 3. And these are empty because you're only having one slack variable per equation. And then we've got a new column for profit. And then our final column are all the actual constraint values. Okay, so now that we've done that, we can just write it all as a matrix. We've labeled the top with the X's and the Y's and the slack variables and all that kind of stuff. And then we've put in all the zeros for the missing quantities. And then it's always a good idea to at least initially label what the rows are, just so you can keep track of things, right? Because now that we've dropped the X's and the Y's and we just have a bunch of numbers sitting there, it's kind of easy for our eyes to blur over and go, okay, what the heck does all this stuff mean? So there, we're going to keep track of, the first one is our land constraint, then our fertilizer constraint, then our labor constraint, and then our objective function, the thing we're trying to maximize, is at the bottom. Do you have to put in these lines? No, but you really should, just to keep your mind's eye organized. Okay, now if we were to graph everything, so from those previous things, we could graph all the equations. Here's the first one. Right? Remember, it's now equals because the slack variables. Here's the second one. Here's the third one. And then, of course, everything has to be greater. Our X's and Y's both have to be greater than or equal to 0. So that's why nothing goes past the axes. And we get this feasible region. And we know that our objective function is going to be maximized at one of the points, right? It's going to be maximized at this point, which usually never happens. This point, that one there. That one there, it's kind of hard to see, or that one there. And obviously, to find all of these, we have to find where these various equations equal each other. You're solving for a set of equations. And that's basically what we're doing with the simplex method. Now, since we've already found these, we can see that our maximum profit here, 1.26 million, happens at this spot, this corner of 3750 and 2250, telling us that we have 3,750 acres of X, remember being corn, and then 2,250 acres of soybeans. And you'll see that that actually adds up to exactly 6,000. So we do end up using all of our acreage. Now, as I mentioned before, the lower left corner, that point that is 0, 0 for X and Y, it's kind of a silly point, right? Because if that happened, then X and Y are 0, which means we didn't use any of our land, and S1, that slack variable, was 6,000. We didn't use any of the fertilizer, so X2 would be the maximum amount, right? And we didn't use any of our labor. And then, of course, the profit would be 0. So obviously, that's not going to maximize anything. But you can also recall that the last row of our thing still corresponds to the objective function of 240x, right? And that should be plus 160y. Let me fix that. There you go, that looks better. And therefore, if we want to improve, our profit from 0, then we want to increase the value of it. And by changing the value of only one of theirs, like so if we were only going to increase the x or if we were only going to increase the y, because the coefficient of x is larger, then the rate of increase is greater by increasing x. So you'd think you'd want to increase x more than you'd want to increase y. Now how this works when we have our numbers in the matrix is, remember, because you take your objective function and you subtract those things to the other side, then the most negative entry in that objective function, that last row, is going to correspond to the variable that is going to give us the most bang for our buck. And that's the one that we want to start with, right? So we're going to look for that most negative value in the last row, and then we're going to pivot, right, on that column, and we're going to call that the pivot column. And so our matrix, our simplex matrix, we're going to call it A, is shown below with the X column highlighted, boxed out, showing that that's going to be our pivot column. The next thing to think about is that, so now we've identified X as being, kind of the most bang for our buck, the most powerful increase we can get per unit. But we also have to think about how much it's limited, and it's limited by the constraining equations, right? The equations 1 through 3 in our matrix. These first three, those are all the constraints. And as we can see in that graph below, that the constraints limit x to no larger than 4,500. Can you see that this is the farthest out that x goes, right? Everything else is behind it. So the largest value for x is out here when y equals 0, and x is 4,500 right here. So we know we can't get any bigger than that, right? So we'll also notice that when you take all the positive coefficients in the pivot column, that first column, and the matrix are divided, you take those and you divide them into the constants in the argument, in the augment, the smallest quotient is 4,500. So again, let me just show you this in math rather than my garbled words. If you take each of these coefficients, each of these numbers that are in our pivot column, and then you take, the equals portions, what we call the augment, because it's an augmented rate matrix. This is the augmented part. We call it the augment. If you take each of these numbers and divide it by their corresponding pair, or their corresponding, thing that's attached to them, 6,000 divided by 1 gives you 6,000. This one divided by 9 gives you 4,500. This one divided by 3/4 gives you 7,000. You can see that 4,500 is the smallest. It also happens to correspond to the largest that x can be, and that's the way it's always going to work. So we're always going to pick the pivot row by getting that smallest quotient. And then that number that gives us that is called the pivot entry, or the pivot. So we're basically going to now pivot on 9. So we found the column by finding the most negative entry. That gives us the pivot column. We find the pivot row by finding the smallest quotient of taking the augments divided by those numbers. And then the intersection of the column and the row gives us the pivot value, or the pivot number, or just the pivot. And the reason, again, why we do that is because that smallest quotient we found of 4,500 represents the maximum amount that x can be increased while we hold y constant at 0. And so that's kind of, the first corner that we're going to go and check. Now what we're going to do is we're going to use our typical matrix methods, matrix operations of multiplying by constants or dividing by constants, which is just multiplying by a fraction, and then adding to other rows to get, a 1 and zeros. And we're going to do that on the pivot. So we want to make that pivot number a 1. So the first thing we would do is we would divide by itself. It's a 9, so we would divide by 9, i.e. multiply everything by 1/9 to make it a 1. Remember, you got to multiply the whole row by that. Then we're going to take multiples of that row and add it to each of row 1 and row 3 to zero those out. So you can see visually, this is what's happening. Once you have zeroed out the first row and the third row, you want to then also go ahead and zero out the objective row, right? Just obviously just that column. We're just hoping to just zero out this. And so this is now our new matrix. We call it matrix B. I mean, it's still the same matrix, but we give it a different number, a different letter because we've changed it. We've augmented it. Now we just repeat the process, right? So we start with the most negative number, which we only have one of them. So now we're going to be in column Y. And then we're going to take each of our augments that have now changed, and we're going to divide them by each of these three numbers, and we're going to see which one results in the smallest number, and that's the next corner that we basically move to check. So you can see that once we've done this work, we get 1,080,000. Well, what does that mean? If we go back to this picture, we can see that that basically corresponds to the point 4,500, right? So all corn, no soybeans. And if we plug that into this function, we get 1,080,000. So we basically have found this first corner point by doing that first matrix set of matrix operations, and the bottom number tells us what the profit is. In essence, right, we have held y equal to 0, and then we've increased x as much as possible. So we started at 0, 0. We held y there. We increased x as far as it could go. We got out to 4,500. We found this first corner point, and then we figured out what the profit was at that corner. And now we're going to augment it, right? We're going to basically transform it again. I should say transform instead of augment word. Transform it again and find another corner piece. Now, if we wanted to stop here, obviously we wouldn't, but if we stopped here, we could see what our slack variables are. We can see that we have 4,500 of our acres spent, and that's not all of them, right? So we're basically leaving 1,500 acres unplanted. We could also go back to the other constraints, plug in the amounts for x and y, i.e. 4,500 and 0, and figure out what our slack variables are for other things. And in this case, we see that we used all of our herbicide, all of our fertilizer, but then down here, we can see that we left some labor on the table, right? We didn't maximize our labor. So with those two things, we're probably thinking, all right, let's keep checking. But in all honesty, we're going to keep checking because the matrix hasn't been reduced, right? We haven't got it in row echelon form. So we need to keep working. But we could also kind of identify all of these variables by looking at our new matrix. And so you can see that, right, this one tells us that x equals 4,500 because we have multiple, right, non-zero things, then y equals 0. Here our slack 1 variable equals 1,500. Our slack 2 variable equals 0. Our slack 3 variable equals 1,875. And our profit equals 1,080,000. So that's how we could glean all of this information just from the matrix. And when we look at these variables that have columns of this type, right, that are basically in a reduced form, not counting the objective function, these are called our basic variables. And then obviously the other ones are called our non-basic variables. And you'll notice that the bottom row, our objective function, has this stuff still in it, right? Negative 80y plus 80 over 3 slack variable plus profit equals this. And if we solve for profit, we put all that, we put this stuff on the other side. And so our profit is actually still depends on y and slack variable 2. So that's another reason why we're not really done. However, those non-basic variables, if we let them equal 0, so that is we let y equal 0 and s2 equal 0, then all those rows put together show us what the other variables equal, and then our solution values correspond to the feasible solution at the corner right down here. and it's called a basic feasible solution. However, if we look at this profit function, right, we go back to the profit function that has these other kind of slack pieces, right? We got the slack variable and we have the leftover y stuff. We can see that our profit can actually be increased by the value of y while holding the value of s2 at 0. So if we hold our second slack variable at 0, this function will increase, our profits will increase as we increase y. And then in matrix B, we can see this fact by observing that the most negative number in the last row, the objective function row, occurs in the y column. Right here. This means the y column is the new pivot column, right? So pivot column, we got to do all of the ratios to find our pivot row. So once again, we do the same work. Take each of these, divide them by each of those. We get these values. You can see that this is the smallest. So now this becomes our pivot row, and this becomes the actual pivot. So we're going to multiply this row by 3 halves, right, to turn this into a 1. Then we're going to take multiples of this row and add it to all 3 of these to make these 3 numbers all 0. And in essence, we're pivoting to the next vertex, right? The next vertice, the next little corner of our feasible region. If we look at the graph again, you'll notice that as we pivot around from this point, which is where we're at, the next closest point is this one right here. I know it's kind of hard to see, but it's these values. And you can see that the value for y is 2250, which is the exact same thing as the smallest quotient, right? So there's a rhyme to this reason, right? There's a reason why we do these things this way. Okay, so let's go ahead and do the operations and get our new matrix. We'll call it C, where we've zeroed out everything, and we're left with these bits and pieces. Now already you should be noticing something about what's left over. Right? What's the first step we always do when we have to transform the matrix one more time in the simplex method? Is we always look at the objective row, the bottom row, and we find the most negative number. Do we have any negative numbers left down there? No. So that means we're done. You'll also notice that both x and y are now basic. The profit function is still basic. Slack variable 3 is basic, who cares? And the other 2 slack variables are non-basic, which also, who cares? But when we're in this situation, we now have our maximum profit function, which you will recall from the table right there. There's our maximum profit. If we look at it algebraically, right, if we take that objective function down here at the bottom, and we solve for profit, we can see that our profit is 1260, and then subtracting multiples of slack 1 and slack 2. Obviously, you don't want to take anything away. So we would just let the slack 1 and slack 2 be 0. Just zero them out. Because otherwise, it would decrease things. Right? It would decrease our profit. Let's put it all together and look at the visual along with everything else. Back to what we saw originally from the graph and from our points, we know that our largest profit occurs here. How do we actually find these points is using the simplex method. When we get to this point, we know we've maximized things because we can't pivot anymore, right? Because we don't have any negatives down here. And it tells us that y, right, equals 2250, x 3750. Put those two together, right? You'll see again that that's all of our land, because slack 1, which is our land, because it's got extra things, we think of it as 0, but we also know that we have to let it be 0, otherwise it's going to end up subtracting from our profit. Same thing with slack variable 2. We're going to let that be 0. But slack variable 3, we actually have 187.5. So we have a little leftover labor. And thus, as we saw graphically, we've now found, systematically, that we plant 3,750 acres of corn, 2,250 acres of soybean, and that's going to maximize our profits at 1.26 million. In this planting scheme, we have 0 unused acres of land, we have 0 unused gallons of our fertilizer, and we have 187.5 unused hours of labor. And that's basically how the Simplex method works, right? It solves this system for us in a very systematic, no pun intended way. So let's generalize it. What are the Simplex tasks, right? What's the task and procedure that gets us from point A to point B? Well, the Simplex method involves a bunch of decisions and operations with these matrices. There are 3 major tasks. Task A is you have to set up the matrix for the Simplex method. You have to basically put everything in the right places in the right form. Task B, you have to determine all the necessary operations and implementing those operations to reach a solution. And then task C is reading the solution from the matrix. Task B is basically a fancy way of saying do all the manipulations to get the matrix in the right form where everything is reduced as far as it can go. And then task C is, from that result, figure out how much of each variable is being used and which ones are 0, etc., etc., etc. Let's look at another example and see how we can apply these tasks to them. So we're given this function 2x plus 3y that we want to maximize, subject to these 2 different constraints. So we first add in our slack variables so we can set them equal to 10 and equal to 14 instead. We move our objective function over and set it equal to 0, and then we would put that into the original matrix, and it would look something like this, right? So here's our original matrix set up with all of our slack variables and constraints. Now we move on to task 2, or task B, which is doing all the manipulations, right? We find the most negative, this becomes our column, we do all the quotients, we find the row, we're now going to pivot on this number, we do the operations, we get this, reduced column and the resulting matrix. We look at these indicators and see that we still have work to do, right? We still have a negative, so this becomes our new column, and we're going to have to do the ratios again to figure out where we're pivoting, which ends up being 3/2 because 6 is smaller than 10. So now we're going to pivot on that spot. That becomes a 1. We got zeros here. And now we notice that all the indicators down here are 0 or positive, so the solution is complete. We've basically found a solution. We've got basic variables x and y, and then our slack variables 1 and 2 are going to be non-basic, so they're both going to be set equal to 0. Right here, y is equal to 2, x is equal to 6, and our profit, right, our maximum profit is 18. And figuring that out, this part 6, is basically task 3, right? Being able to identify what the matrix is telling us. Let's try another example, doing our 3 tasks. Here's the thing we're trying to maximize, our objective function. Here are our constraints. Put in our slack variables so that they're all equal, right? Put this stuff to the other side. There's our setup. Identify the most negative, and then our smallest ratio. This becomes our pivot point. And you'll notice that every time we set these things up, x and y are by default non-basic, right? Because they have other non-zero numbers in their columns. And this always corresponds to the basic feasible solution of x equals 0 and y equals 0, basically always starting at that lower left-hand corner of your feasible region. And then it also ends up corresponding to your slack variables, right, being the leftover bits of the constraints. Basically, everything is going into slack. And then also, your profits are at 0. So like I said before, it's a solution, but it's a stupid one, right? We call it it's called usually a trivial solution because it works, but it doesn't really work. Okay, so we do task B, or we start into task B, and we reduce the first column, and get this new matrix, we notice that we still have a negative number down here. So we repeat the process. This becomes our pivot column. We check our two ratios, our two quotients, right, our two fractions, and we find the smallest one here, and we pivot on that to get our next transformed matrix, which is this one. And now we can see that there's no negative indicators in the last row, so the solution is complete. We can see that y is 2, x is 4, our profit is 22, and both of our slack values are 0. How do we know when we have non-unique solutions, meaning we can get multiple solutions or no solution at all? Well, let's look at an example and see when we can kind of identify when it's happening. Here's our function we're trying to maximize. Here are our constraints, right? Everything is still following the rules. If we were to graph it, we see that we have a feasible region. Everything, seems to work just fine. We put it into the matrix. We have our biggest negative, not our biggest, but our smallest negative, right? So we have a pivot column. We do the 16 divided by 1, 24 divided by 1. Obviously, this is the smallest one. That becomes our pivot element. We pivot, and then we're immediately done. There's no more negatives left. And thus we see that our function is maximized at 32 when x equals 16 and y equals 0. When this occurs, when we get our variable, not a slack variable, when we get our variable with a 0 indicator, then we can often use that column with the 0 indicator as our pivot column, and it'll often give us a new solution that has the same value for the objective function, i.e. it will maximize the objective function at the same way. And in fact, if we do it, we would come up with x equals 8 and y equals 16, and we would get the same optimal value of 32. So we can see that when we have an optimal value of f, which we have right here, right? And it has a non-basic variable, this one right here, non-basic, right? Because it doesn't have a 1 and a 0. And it has a 0 indicator in its column. Then that tells us there may be multiple solutions, giving the same optimal value of, in this case, 32. And we can discover whether another solution exists by using the column that has the non-basic variable and the 0 indicator as our pivot column. And we would do the same thing, right? 16 divided by a half is 32. 18 divided by a half is 16. We would pivot here and do the work and end up coming up with the same answer of 32. What about no solution? Well, it is possible for a linear programming problem to have an unbounded solution and thus no maximum value. If we have something like this set up where everything seems to be right. We've got a thing to maximize. We've got our objective functions that are less than or equal to positive numbers, so we think we should have a nice little complex system. We set up our system. We find our smallest negative. We find our pivot. We pivot. We still have a negative, right? And we're thinking we're good to go. However, when we go to find that pivot entry, we see that both of the rows give us the smallest quotient of 3, because 3 divided by 1 and 6 divided by 2. Thus, if we just pick the first one and do the work, we get this simplex matrix. And if we use that most negative number as our pivot column, we notice that there is no positive coefficient in this column, right? We only have a negative 3. So even if we could pivot using the x2 column, the variables x1 and s1 would remain equal to 0, and the relationships among the remaining variables would still be the same. Because we can see as x2 is increased, right, down here, that forces x3 to also increase because all of our variables are non-negative. This means that no matter how much we increase x2, all of the variables remain non-negative. And furthermore, as we increase x2 and therefore x3, the value of f also increases. And so we can see that this is kind of a perpetual machine, and it just goes on to infinity. So how do we identify this? Well, if after the pivot column has been found, there are no positive coefficients in that column, then no maximum solution exists. It's just that simple. So as soon as we got to the matrix here, where this is supposed to be our pivot column, but we didn't have a positive number anywhere up here, then we know no solution exists. So that's the easy way of seeing no solutions, and we saw the same easy solution for multiple solutions. The last thing to talk about are shadow prices. And we note that one of the most powerful aspects of this simplex method is it not only gives us, the solution to the problem, but it also tells us how we can adapt that given solution whenever the situation changes. Particularly from that final simplex matrix, that what we call the final tableau. The solution to the problem can be read. We can see, what our profit function is and, how much of our constraints are being used. And it tells us the amount of change in the objective function that we would get if we added one additional unit of a resource, right? If all of a sudden we had another acre to plant in our soybean and corn example, then we could see how that would change based on the coefficient of, an acre of corn or a coefficient of an acre of soybean. And so that's called a shadow price, and how this additional resources changes the optimal solution values. So that's the last kind of aspect that we're discussing in this video, and that's all.